Alright, a big part of Chapter 4 for us is curve sketching. So here's a curve. No calculator allowed. Alright, I am sure I would ask you for all the critical points, all the points of inflection, all the regions where it's increasing, all the regions where it's decreasing, all the regions where it's concave up, and all the regions where it's concave down. So we're just going to go through this step by step. If I'm going to graph this, the first thing I want to do, even before I take the derivative, is find the zeros. Guys, do you agree the zeros in this case for this function are 0 and negative 4? And that's also the y-intercept then, right? You plug in 0 for x, y is 0. That's just helping us set some points on this graph. X to the fourth plus 4x to the third. I think to myself, hey, what happens as the limit as x goes to infinity? Obviously, this is getting bigger both ways, to negative infinity and positive infinity, because it's not divided by anything. And then I say, hey, all right, let's do some derivatives. Gosh, try not to make a mistake here, and I should talk. You guys know I sometimes make errors. Everybody does. And I take a second to make sure I didn't screw up here. I don't think I did. And now I would say critical points. And the key part here is a critical point, all right, when you define it, it's not just where y prime is equal to 0. It's also where y prime is undefined, both parts. In this case, it's pretty easy, again, to see that the critical points are at x equals 0 and negative 3. Now I'm interested in the points of interest, which might be points of inflection, where the second derivative is equal to 0. So I look at the unfactored derivative, and I find y prime prime, which is 12x squared plus 24x, where y prime prime is 12x comes out, right? X plus 2. And I know y prime prime equals 0 at x equals 0 or negative 2. All right. If I had a rational function, I would include any asymptotes. This is a polynomial. Its domain is all reals. We knew that immediately. I don't know the range. Don't care. All right. Don't want to take time to figure it out. I would now take all of this information, and I guarantee this would be a whole page. You'd have a question at the top and just a blank page. I'm going to now set this into a table. All right. I always make my tables the same way. Most professors do that I've seen. Not to say there aren't some other ways. But I am going to figure out the sine table for my derivatives. And I like calling this known. All right? And the numbers in my sine table are simply going to be, and I'm not going to put in the zeros, are just going to be the critical points and the places where the second derivative is 0. All right. So I got negative 3, negative 2, and 0. And I'll fill in my zeros right away. 0 and negative 3 are the first derivative. So hopefully you see that you have 3 sine regions to determine. You guys see that? And likewise, if I put my zeros in for the other derivatives, 0 and 0, you see there's also 3 regions in the second derivative to figure out the sine up in the green. All right? I'm going to get rid of the green boxes. I don't put those in usually, all right? We're going to fill in our sine table now and figure out the sines. Now, because this is a polynomial, the second derivative rule is really slick. So I'm going to figure out the sine of my second derivatives, all right? So I look here and I say, hey, I put in a negative number way to the left of negative 3, or way to the left of negative 2, right? And I think of like negative 1,000. I put it in here. Well, negative 1,000 squared is positive. Don't care about 24x. This has to be a positive. I usually then, when I see a parabola, 12x squared plus 24x, I jump to the other side, put in 1,000. You see that this is going to be positive, right? And you pretty much inkle, all right, that the in-between is going to be negative. I would put negative 1 in and check. 12 times 1 is 12. 24 times negative 1 is negative 24. 12 minus 24 is negative. Guys, I now know my intervals of concavity. Yep. And I also know my 2 points of inflection, because there is a sign change across these. It's not because the second derivative is 0. It's because there's a sign change in the second derivative. Okay? So my points of inflection are -2 and 0. All right. If I ask you for the point, what do you have to do to get the y coordinate? Plug it back into the original function. All right. So one of them's real easy. There's a point of inflection. That's 0, 0. All right. And there's a pi here at. Now this is my favorite cheat. You guys ready for this move? Isn't that the y value? F of -2. And I'll usually let you get away with that move. All right. Yeah, to plot the point, sometimes it's real helpful to know. That said, I do not have to figure out the signs on the first derivative by plugging the numbers back into this. All right, I don't have to, okay? What you probably should catch up there, all right, is that I have a negative number here, all right? And I have a, because if I go back up in here, guys, if I go back up in there, right, a big negative number, 4x squared is always positive. So it's just a negative number. Then to the right of -3 is positive. And here it is also positive. Now this is the one that gets you. You guys sometimes get so used to alternating signs. This is a nice problem, right? This only has a negative to positive sign change. A negative to positive. First derivative rule would tell you negative to positive is a local min. The second derivative rule would say, hey, it's 0 and it is concave up, therefore it's a local min. I don't care which rule you justify it by. Local min, and I would go negative to positive, first derivative rule. The other option that you could have wrote was f prime equals 0, f prime prime is greater than 0. That would also be second derivative rule. All right? Everybody, this takes practice. You got to do some of these, all right? Or at least read them. You have to be able to define the first and second. Everybody, here's what gets students. This is not a max or a min. It's nothing. It doesn't change sign. There's no sign change in f prime. And when the first derivative is 0, what's the second derivative? 0. It's not positive or negative. It is not a max or a min. So now I can define, I think, all my regions of increasing and decreasing, all my concavities. Let's do that first. Increasing, decreasing. We'll do those separately. And then we'll do concave up, concave down. Increasing, I think it's just between -3 and 0. I think it's decreasing from -infinity to -3 and 0 to infinity. No. Wait a minute, what am I doing? I screwed up. This should be up here, right? It's positive. Does that make you guys feel better? Right? My bad. Now, on the next one, concave up. 2 spots. Concave up where the second derivative is positive. So I was looking at that region. How about -infinity to -2 and 0 to infinity. And it's concave down where it's negative. So -2 to 0. All right? Everybody, I've defined critical points. Points of inflection. Increasing, decreasing. The concavity. The last thing you can do with this is sketch the function. All right? This takes... try to make this one thing. I would set the points of inflection. This is why, Megan, this is why you probably said, isn't it easier just to have it? Yeah. I would set my x and y axis. And I know it goes through 0, 0, 1, 2, 3, 4, 0. I know it had a local min at -3. And I know it's decreasing. Everybody, you should be able to tell that the limit's and increasing. Very beginning. Oh, -4. Shoot. My bad. Nice catch. There we go. So it's coming in the -4. And I know it has a minimum at -3. You guys agree if it's 0 here and 0 here, -3? I don't know what it is, but it's got to be below the x-axis to be a minimum. All right. You know it's decreasing all the way to -3. It's decreasing all the way to -3. And it's 0 at -2. That's going to be weird. At -2, it's not increasing or decreasing. Concave up here has a point of inflection at -2, and it switches, or for an instant. Oh man, I butchered that. And then it goes concave down, concave up, and again, there it is. All right. And then what? At 0, it goes back to concave up. Guys, what it's got is a little kind of inflection point at 2, right? Where it's not increasing or decreasing for an instant, where it makes that break. And if you want to see a great picture of it, type in your graphing calculators. I wouldn't expect to sketch better than this. I might not even ask you for the sketch of this. All right? What for sure we would do, if I was to tell you about the problem, it would be in my classroom, probably 30 to 40 points here, 30 to 40 points here. If I make a graph, it'd be only worth 10, where everybody in my room knows that X and Y labels are worth 3 points. So pretty easy place to live, right? All right. Everybody, test tomorrow. It will be broken into 2 parts. You'll have some time on Thursday. All right. Keep practicing.